Hey everyone, here's the warm-ups for our lesson 4.08, talking about inflection points. I want to get your mind going before we get into that lesson. So let's go ahead and talk about these warm-ups. Number one, it says draw a graph that has the following properties. So I want to go ahead and write this out. Number one, it says that f of x is less than 0. Now, we talked about the other day the idea of the difference between a function being positive and a function increasing. And so f of x is less than 0. What does that mean? F of x is less than 0 means that the function is below the x-axis. So I'm just going to put in parentheses, therefore f is below the x-axis. Okay, so that's what this tells me. Now it also says that f prime of x is greater than 0. Well, we can interpret that based on our chart. We know that f prime of x is greater than 0. Well, what does that mean for f? If f prime is greater than 0, in other words, f prime is positive, we know that f is going to be increasing. Okay, and the last part, it says that f double prime of x is less than 0. So just the last lesson, we talked about this idea of concavity. Concavity is the trend of the function. Is it trending in an upward manner or is it trending in a downward manner? So we learned that the relationship between the second derivative and the function is the concavity. So if f double prime is negative, then f is going to be concave down. F is concave down. So we are looking for a function that is strictly below the x-axis, strictly increasing, and strictly concave down. So sometimes this can be a little bit tricky to draw. This particular function is going to probably have an asymptote to it because it is always these things. So we have to stay below, we have to stay going up, we have to stay increasing, and then we have to be concave down. Well, somebody might say, how can you always go up? How can we always increase without ever crossing the x-axis? Well, because of the concavity here. We are trending downward, so we have something that looks like this. A function that looks like this. So we can see that we have a horizontal asymptote at y equals 0. This function is always below the x-axis, it's always increasing, and it's always concave down. So that's a great example of one of these types of problems, or one of these types of functions. Number 2 says y equals 5 minus x to the 1/3. And it's asking for when the function is concave up and concave down. So again, the idea of concavity is related to the second derivative. So we're looking for when the function is concave up. That means we're looking for when the second derivative is positive. So we have to take the second derivative. Well, the first derivative is going to be negative 1/3 x to the negative 2/3. And then the second derivative is going to be equal to 2 over 9 x to the negative 5/3. So we're just using the basic power rule on this type of problem. Now I'm going to go ahead and simplify this so I don't have negative exponents. That just kind of makes things a little bit more confusing. The second derivative is then 2 over 9 x to the 5/3 in the denominator there. Okay? So we need to look for when this function, this second derivative, is positive and negative. So we're going to go ahead and figure out not our critical points, but our points of interest. We're going to go ahead and look for when the second derivative is 0, and we're going to look for when the second derivative does not exist. Well, if I set the second derivative equal to 0, and go to solve this, we would immediately say that the second derivative never equals 0, because you could cross multiply here, you would end up with 0 equals 2, which does not exist, or there is no such values for it. That's true. But now we're looking for other points where the second derivative can change signs. So we're going to be looking for when the second derivative does not exist. So y double prime does not exist when, well, how do we know a function does not exist? A function does not exist when we divide by 0. So we would set the denominator equal to 0. So we'd say when 9x to the 5/3 equals 0. So just a kind of a clarification, if the second derivative is equal to 0, that would imply that the numerator has to equal 0, because 0 divided by anything is 0. But if the second derivative does not exist, that would imply that the denominator is equal to 0, because then we would have a number divided by 0, which does not exist. So when does this equation equal 0? When does 9x to the 5/3 equal 0? Well, that's pretty simple. We can divide by 9 if you want to, so we get x to the 5/3 equals 0, and then we could raise this to the 3/5, but however you look at this, the answer to that question is x equals 0. So we know that the second derivative, we're going to set up our number line now, when x equals 0, the second derivative does not exist. And normally we have zeros up there, but that's the only point of interest. That's the only point that we consider valuable here. Now, we're going to check the signs of the second derivative on either side of that x value. So we'll plug in any negative number here. If I plug in any negative number to x, well, the cube root of a negative is a negative. And when I raise a negative to the 5th, I get a negative. So I got 2 over 9 times a negative. That's going to end up being a negative value. And now I'll plug in a positive value for x. Well, a positive number raised to the 5/3 is positive, so this whole thing is going to be positive there. There we go. We now know when the second derivative is negative or positive, and we can conclude as a result of that, we could say that y is concave up over the interval 0 is less than x is less than infinity, since y double prime is positive over this interval. Okay, so that's where we're concave up. Now, y is concave down over the interval negative infinity less than x less than 0, since y double prime is negative over this interval. All right, so now we've identified the places where the function is concave up or concave down. And that's going to lead into the lesson of points of inflection. Points of inflection, just a quick idea, is when the second derivative changes signs or when the function changes concavity. So this is a good warm-up to kind of lead into that idea. So stick around for the next lesson. Hopefully you can get something out of it. Hopefully this helps you solidify your understanding about concavity and other basic concepts of calculus.